Today we're looking at using similar polygons in order to talk about the relationships of geometric figures. Similar polygons are similar if the corresponding angles are congruent and the corresponding sides are proportional. So two kind of important things there. If you were to mark these down, you want to talk about the corresponding angles being congruent. Corresponding angles are congruent. And secondly, the corresponding side lengths, they're not congruent, but they're proportional. If they were congruent, we would then not have similar figures, but we'd have congruent figures. Corresponding angles are congruent, and the other sides are proportional. What we're dealing with is we're basically dealing with some big shape, some small shape. They look very similar, but one's just small, one's big. So the way this is related with our translation or our transformations we've been talking about lately, basically these are a dilation of one another. Here's the big version, the enlargement. Here's the shrinkage when we compare these two figures. Notice there's a symbol in between this symbol right here, which stands for similar. You'll see it up here. ABCD is similar to EFGH. Is how we pronounce this. We compare all the corresponding angles, so we compare A to E, we compare B to F, C to G, D to H. What makes this a little complicated is not always will they have these in the exact same orientation. Every so often they will rotate one of these shapes just a little bit to make sure that you have your geospatial sense. We can also talk about a ratio of corresponding sides, or a ratio of proportionality, talking about the sides being proportional. We'll take a look at, we'll try to simplify this all the way. If we had numbers in here, we could simplify these. All these should simplify to the same fraction, whether it's 3/4 or 1/4 or whatever it might be. They should simplify all to one fraction, and this one fraction will be called a scale factor. Let's look at our first example. It says list all pairs of congruent angles. All I really need to do is look at this statement of proportionality here. To look at this, then I'm going to say that angle R is going to be congruent to angle X. I'll say angle S is congruent to angle Y, and then finally angle T is congruent to angle Z. This is given to me right here with our similarity statement. That's how I know what my congruent angles are. I think it's a lot easier than trying to dig this all from this these triangles in the picture. Check the ratio of corresponding side lengths. So I'll say I'll compare 25 and 15. Hopefully that'll be equal to 30 over 18. And hopefully that'll be equal to 20 over 12. I'll simplify these fractions. Both these are divisible by 5, so I'd have 5/3. Both these are divisible by 8, so again, there's 5/3. And both these are divisible by 4, and I'll have 5/3. Notice all of these will simplify to the same number. That's 5/3. That is going to be our scale factor, which we'll introduce very soon. It's our scale factor. It's also going to be our ratio of side lengths. It's also going to be our ratio of perimeters. And we'll see how it relates to the ratio of areas later in this lesson. Finally, part C says write the ratio of corresponding side lengths in a statement of proportionality. All that means is I'm going to compare these. Again, I'll look at my similarity statement in order to write this. So I'll just say RS, these are the first two letters, over XY, those are the second two. I'll say the second two letters, ST, over the second two up there, that'd be YZ. And finally, the first and last RT divided by XZ. If you notice, this should be pretty similar to what I wrote up here. All I was doing was I was comparing side lengths as I went along. So this is our statement of proportionality. It's basically in general form from the similarity statement. You're writing the ratio of the side lengths separately, each one of the side lengths. Okay, multiple choice triangles ABC and triangles DEF are similar. What statement is not correct? This looks good. We're using the first two letters over the first two letters equals the last two letters over the last two letters. This is first and last over first and last over first and second over first and second. Those look fine. What's not okay with this is the first letter. This is the third letter. We could write angle A is congruent to angle D, or we could write that angle C is congruent to angle F. We don't necessarily know that angle A is congruent to angle F. So I'd say this one is not necessarily correct. Next, we're talking about scale factor. If two polygons are similar, then the ratio of their lengths of the two corresponding sides is called the scale factor. In example 1, which we just done, the common ratio was 5/3, so the scale factor between those two shapes. And again, if two figures are similar, they're always going to have the same scale factor. So it's one way that we can actually check whether two figures are similar. Determine whether the two polygons are similar. Oh, we'll have to do that using the scale factor. Very convenient. If they are, write a similarity statement and then find the scale factor. So what I'll do is I'll take one side length here, 5/6. I'll compare the similar sides here. I'll compare that to, okay, 5/6, that's fine. And I'll compare that to 3/4. If these are all the same, we're fine. Well, is 5/6 the same as 5/6? Well, it is. Is 5/6 the same as 3/4? It's not. So are these two figures similar? No, they're not. Okay. Over here, we'll compare 4 to 16. These would just be sort of the heights of these two rectangles. And we'll compare that to, say, 6/24, which would be the widths of the rectangles. I'll simplify both these fractions. These are both divisible by 4, so that'll give me 1/4. These are both divisible by 6, also gives me 1/4. This becomes my scale factor. It also becomes my ratio of side lengths, fully simplified. I also need to write a similarity statement, so I would say something like WXYZ is similar to, I started over here at this point talking about a length of our rectangle, so I'll just do this over here. That'd be DABC. Okay, it's not necessarily just alphabetical order and alphabetical order. That's why this example exists, to say that sometimes they'll mix these around on purpose so that you don't always write them in alphabetical order. You need to watch the order. That similarity statement does matter. Theorem 6.1 talks about the perimeters of similar figures. We already talked about how the lengths of corresponding sides are going to give you the same. This is our statement of proportionality, saying that these lengths are going to be related. Well, the same thing happens too if I add those four lengths together. I'll get the perimeter, that's this top part here, and the perimeter of this guy. Since the perimeter is basically just a length, they're also going to be proportional. So it'll be the same thing as the scale factor in ratio. In the diagram, WXYZ is similar to MNOP. Notice that I have to kind of rotate this guy just a little bit, maybe in my head, or rotate this guy just a little bit in my head, just so that I can kind of see these two right next to each other more easily. Find the scale factor. The only two sides that I know here are going to be this 8 in comparison to this 10. So when I try finding the scale factor, I'll say 8/10. I'll simplify it as best I can. They're both divisible by 2. So my scale factor is going to be 4/5. It is important that you do simplify. Next, I need to find the value of x. The value of x for me. What I'll do is I'll just set up a ratio here. I'll use my scale factor, 4/5, and I'll compare that to 12/x. Notice 12 is my length on top, x is my length on top. I'll cross multiply, I'll have 4x equals 60. When I simplify, x will just equal 15, whatever those units are. So that's x. Again, I'll use the same ratio, 4/5, and I'll say that's going to be y/10. I'll cross multiply over here, so this would be 5y equals 40. I'll divide both sides by 5, and y equals 8. Running short on room here. We'll talk about z. Well, that's not a z at all. There's z. Z is this angle right down here. I can only compare it to this angle here. Z simply equals 135 for the degrees. So let's find the perimeter of WXYZ. Well, if this is 12 and this is 8, this is 12, this has to be 8. We'll go around 12 and 8 is 20 plus another 20. This would be 40 units. The perimeter right here, we know this is 10, this is 15, that's 25. 10 and 15 again is 25, so that would be 40. Find the ratio of the perimeters. That would be 40/50. When I simplify that, again, the ratio of perimeters is going to be the same as my scale factor when I simplify it. Okay, something to keep in mind, that the ratio of perimeters, again, is just basically one of the lengths. So each one of the lengths is going to be in proportion It's going to all be related to our scale factor. How's similarity related to congruence? Okay, things can be similar, things can be congruent, sometimes they can be both. Notice that any two congruent figures are also similar. Notice that we could say 5 over 5, 7 over 7, 6 over 6 in our statement of proportionality. When we simplify that, all that will simplify down to is 1. We have a scale factor 1 to 1, or just a scale factor of 1. You can write that these two triangles are similar. You can also write that they're congruent. This is a more specific statement which does tell you that they are similar. So if I was to write just one of these, I would pick to write the one that says that they're congruent. You know, the perimeters of similar polygons are in the same ratio as the corresponding side lengths, so you can extend this concept to other segments. Basically what that's saying is that if you know the scale factor, you also know the ratio of any lengths in a triangle, such as side lengths, such as altitude, such as mid-segments, such as medians, and so on. So any relation of lengths is going to be related to the scale factor. Let's start applying these concepts as we look forward. When we look at these two pieces right here, we'll notice just one thing that they have in common is the 6 and the 12. So right away I'm looking at, if I had a scale factor, it would be 1/2. So everything is going to be 1/2 of the other piece. So for me, I'll set this up. Again, I'll use 1/2. 1/2 is going to be related to n over 8. I'm always talking about the small side to the big side. So 1/2 to n over 8. When I cross multiply it, I have 2n over 2n equals 8. When I divide both sides by 2, n equals 4. In order to find m, I'll use the same thing. This would be 1/2 equals, this would be 5.5 over m. When I cross multiply it, I have m equals 11. So I know that this length right here is 11. I'm showing you this setting up a proportion because that should be something familiar to you in Algebra 1 using the cross multiplication method. Should be pretty familiar to you. This problem over here is just a little bit more complicated. Again, we'll find our ratio of side lengths again. So this would be 15 over 10, or if we simplify this, this would be 3/2. 3/2 becomes my scale factor, so it makes really good sense that I can then compare other side lengths using it. The tough part is when I use this m plus 4, I need to make sure that it stays together. So when I cross multiply here, I'll have 3m on one side, and I'll have 2 times m plus 4 on the other, or in other words, 2m plus 8. So be careful with that. I'll move the m's to the other side, and m will just equal 8. That way I could also say that this side over here equals 12. Similar triangles, says triangles RST and WXY are similar. Side lengths of triangle RST are 10, 14, and 20 inches long. Length of the altitude is 6.5 inches. The shortest side of this guy is 15. So the shortest is 15, the shortest here is 10. That automatically gives me an idea that my scale factor should be 10 over 15, or basically we're dealing with 2/3. Everything is going to be compared to this 2/3 now. So if I was to find the other two side lengths, I'd just say 2/3. I'll have 14 on top. Let me just give you an x here for the other part. I'll cross multiply. That'll give me 2x equals, let's see, 14 times 3. 14 times 3. 14 times 3. I don't know what 14 times 3 is. Let's see, that'd be 30, 50, 42. 42. Divide both sides by 2, and x equals 21 inches. So that's one side length. Again, we'll use 2/3, and we'll say, let's see, this other side length is going to be 20 over, we'll say this is y. If I cross multiply, I have 60 equals 2y, or y equals 30 inches. So those are the two side lengths. Find the length of the corresponding altitude. Again, I'll use 2/3. One altitude is 6.5, the other we'll just call it z. When I multiply 6.5 times 3, 6.5 times 3 is 19.5. This is 19.5 equals 2z. I'll divide both sides by 2. If this was 20, it would be 10. So this should be 9.75 equals my z. Again, this is in inches. It's my other altitude. Any questions? Okay, moving right along. In the diagram, x, y, z, and m, a triangle M and P are similar. The first thing we want to do is we want to find the scale factor. So if we look, we can only really compare these two sides here, the 4 and the 10. So the scale factor will be 4 over 10. When we simplify that, both are divisible by 2. So our scale factor is going to be 2/5. Next, there's our scale factor. Find the unknown side length. So everything is going to be compared to 2/5. 2/5. We'll start with the bases. So we'll say that'll be 6 over x. Make sure that this is the small triangle, this is the big triangle. Make sure that you put the small thing on top and the big one on the bottom. We cross multiply. We have 2x equals 30, or x equals 15. We'll again use 2/5. We'll use this to find the right sides. So we'll say that'll be, I don't know, y over 9. When we cross multiply, we have 5y equals 18. Or when we divide both sides by 5, 5y divided by 18. 18 divided by 5, I mean, that should give us 3.6. Okay, let me just label this up here. This is 3.6. Down here, this base again was 15. Number 18 says find the length of the altitude. Again, I'll just use the 2/5 business here. One altitude that I have, I don't know what this one is, so I'll just give it a variable of z, and we'll say this is 5.8. I'll multiply both sides. That'd be 11.6 equals 5z. I'll divide both sides by 5. I should get 2.32 as my altitude over here. 2.32. Wow, that barely fits in there. Now it says find and compare the areas of both triangles. Okay, well, area of a triangle equals 1/2 your base times your height. So we'll start off with the small one. That'd be 1/2. Our base was 6 and our height was 2.32. Luckily, I kept all those numbers for exactness sake, I guess. That would give me 6.96. The area of the big triangle, then, still area equals 1/2 base times height. That'd be 1/2. My base is 15. My height, kind of a funny number, 5.8. Ha ha ha, it's funny. We'll get that to be 43.5. Now it says what we want to do is we want to compare these. Well, one thing to think about, these are feet squared and feet squared, or inches squared and inches squared. These are basically going to be areas. Everything I've talked about so far, all these numbers up here that are circled, are basically ratios of lengths. And we're now going to compare ratios of areas. It should not be the same as 2/5, but it should be related to the 2/5. So let's compare these. We'll say, let's compare these like so. 6.96 over the 43.5. When we simplify this, we get 1.16, which doesn't really tell me a whole lot unless I write it as a fraction. As a fraction, this is actually 4/25. Now that might not mean a whole lot to you, but if we look at our ratio of side lengths to the first power, that's just going to be 2/5. But if we take 2/5, and since we're dealing with areas and everything is squared or two-dimensional, when we square that, that's going to be 4/25. So this talks about our ratio of areas is 4/25 as related to our ratio of any length, which is 2/5. It's always going to be a square. If I was to take this one step further, I'll just try to extend the page. If I was to talk about a three-dimensional object, I would basically take 2/5 and cube it. That would give me 9/125. This would be the ratio of volumes. Ratio of volumes, ratio of areas, and then our ratio of side lengths right there. Finally, let's talk about this swimming pool. Kind of a nice story problem to end with. Nice warm weather we've been having lately. It's good to think about the community pool. Think about this. It says that it has a rectangular swimming pool. This is our swimming pool, I guess. And around it, there's some sort of fence. and it does say that these two are similar to one another. It gives us some of the dimensions. It says the shape of the pool is similar. The pool is 30 feet wide, 30 feet. The fence is 50 feet wide and 100 feet in length. Something that freshmen and sophomores need to really remember is that when it says long, that's going to be our longest side, or our length is going to be our longest side. Our width is then going to be the shorter side when we talk about rectangles. So this is the width, this is the length, width and length. Make sure that you do set them up correctly. What's the scale factor? We'll just say 30 over 50. Really easy to simplify down to 3/5. This is our scale factor. What's the length of the pool? We'll use our scale factor. That's 3/5. We don't know the length of the pool, but we do know the length of the fence is 100. We'll cross multiply, that'd be 5x equals 300. When we divide both sides by 5, we get 60 feet. Okay, so this length right here is 60 feet. Next, find the area reserved strictly for sunbathing. Well, this is the pool right here. And so what we're doing is we'll find the entire area of the fenced-in area, and we'll subtract this pool area because people can't really sunbathe strictly in the water because they might be, you know, splashing each other or doing whatever else they might be doing. So we'll just find the two areas. Area of the fenced-in area will just be 100 times 50, or that'll be 5,000 square feet. The area of the pool would then be 60 times 30, which equals 1,800 square feet. We'll subtract these two numbers to get the remaining area, which should be 3,200 square feet. We're looking at similarity as it relates to the ratio of similar figures, I guess. So similar polygons, remember that the corresponding angles are congruent. The corresponding side lengths are always going to be proportional. Setting up some sort of proportionality or statement of proportionality.